Right, so we're just going to look at a whole heap of techniques for different types of trig integration, how to approach different situations. So we're going to start off with, well, obviously we know the standard ones already. So we know how to do, or should know how to do these ones. So we know sine goes to negative cos. We know cos goes to negative sine. We know sec squared goes to tan. We hopefully know tan, and if you don't remember, you can rewrite tan as sine on cos. But tan goes to minus the log of cos or the log of sec, depending on whether you like negatives or not. Okay, so they're our standard ones that we know already. So now, what happens if it's sine to the power of something or cosine to the power of something? I'm only going to look at the sine to the power of ones because the technique's exactly the same for the cosine ones. So, sine to the power of n. Well, let's start with sine to the power of 1. So again, standard integral, nice and easy, minus cos. Sine squared, we've seen that one so far. That's where we need to use our double angle result and rewrite sine squared as a half of 1 minus cos 2x. And then we can go and integrate both of those. So we've got half of x minus half sine 2x. Sine cubed. All right. I'm going to rewrite sine cubed as sine x times sine squared. Then the sine squared I can change to 1 minus cos squared. And now I can do a substitution. I can go u equals cos x. So I go u equals cos x, du is minus sine x, so I can create, it'll end up being minus the integral of 1 minus u squared. And so we get minus, or I've moved it around, so a third u cubed minus u plus a constant, sub the cos back in. So whenever the power is odd, that's what I'm going to do. I'm going to factorise out to the power of 1. That will end up becoming my du. But because it's to an odd number, that'll leave me with sine to the power of an even number. And that even number I can always write as sine squared to the power of something. The sine squared I can always change to 1 minus cos squared, and then I'm right. Because I can substitute in for the cos, but remember I factorised out the sine, which will end up being the du. So that's an odd power. Let's look at sine to the power of 4. Can't do it with sine to the power of 4, because with sine to the power of 4, if I pull it out, I'll be left with an odd number. So I can't write it as sine squared to something nice. So this one I'm going to write as sine squared squared. And then the sine squared, I'm not going to write as 1 minus cos squared, but I'm going to use our double angle result. So I now have a quarter, half squared, 1 minus cos 2x. Then I expand that out, and each of these I can now integrate. I can integrate the 1 easily, I can integrate the cos. Well, cos squared 2x will now become a half of 1 plus cos 4x, and eventually we've now got something, well, I'll just add the 1 and the half together there, so we've got 3 on 2. Now each of those can be integrated. So for an even power, I will always write it as sine squared squared, but I won't use the 1 minus cos squared, I'll use the double angle result. And that will allow me to expand out, and basically I'm lowering the power. Now I might have to use, depending on what the power is, I might have to use another technique to go and do the next bit. So if we've got a really high power, there could be a lot more work to do. So I think personally the odd powers are easier than the even. So here's another odd one, sine 5, as I say. Pull the sine out, I can write that as sine squared squared, sine squared 1 minus cos squared, u equals cos x, sub it in, and we get a fairly simple integral to do. Bingo. Whereas sine to the power, I don't think I bothered with sine to the 6, did I? Too much work. Sine to the 6 would be sine squared cubed, then I'd have that expansion and I'd have to do each individual term. Alright, what happens if we've got a combination? So not just sine, but you've got sine and cosine to different powers. Most of the time we'll end up with just a simple substitution. U equals sine x or u equals cos x. So here's one where both the powers are odd. Now if they're both odd, then I can pull out either a sine x or a cos x, which will then make that even. So I've pulled out the sine. I always tend to pull out the lower power. So I'll pull out the lower one, pull out the sine, The sine cubed becomes sine squared times sine. The sine squared I can change to 1 minus cos squared, and now I can do a simple u equals cos x and sub in. So u equals cos x to u is minus sine x, and there we have it, u to the power of 5 times 1 minus u squared. Integrate that, comes out quite nicely. So if they're both odd, you have a choice. I could have done it by factorising out cos x, and then I would have changed the cos to the power of 4 to be cos squared squared, and write the cos squared as 1 minus sine squared, and do a u equals sine x. And it would have worked just as well. Both odd, it doesn't matter which one you end up using as u. Usually the higher power will end up being the u, because it's the lower power that you factorised out to create the du. Okay, one odd, one even. Well, as long as one is odd, I'm okay, because I can always pull out to the power of 1, leaving me with an even power. So that's what I'm going to do. I'll pull out the cos x, which will leave me with cos squared. Cos squared I can turn into 1 minus sine squared. Bang, I can do my substitution. U equals sine x. So u equals sine x, sub in, and there we are. So as long as there's an odd power in there, these are pretty easy to handle. Right, so odd that, so the even one will end up being the u, because the odd one you've pulled out the du. Well, what happens though if they're both even? So I'll do sine squared cos squared. So I can't pull out a cos, I can't pull out a sine. There's different ways of doing it. I could rewrite this as sine squared 1 minus sine squared. And then I've just got two trig integrals to do. All right, sine squared, well, we know how to do that. Sine to the power of 4, well, we've got a technique to do that. And so I'll just do them each individually. And there's my answer. I'm cheating a little bit because we've, of course, already worked out sine squared previously, and we worked out sine to the power of 4 previously. There's another way I could approach that. Don't know if I put it in the notes or not. What's another way I could do that? Yeah. Because those powers were the same, I could make that as sine x cos x all squared, and then change the sine x cos x to be a half of sine 2x. So I could have done it that way as well. And there's my final answer. If those powers are the same, that gives me another way. If they weren't the same, like if I had a 2 and a 4, then that idea probably is not going to work, because I can't create the sine 2x. So usually, okay, we'll make sine squared equals 1 minus cos squared, or cos squared equals 1 minus sine squared, and break it up into individual trig integrals. And we've seen the techniques to do those individual ones. All right, let's have a look at tan. So tan to some power. Tan to the power of 1, hopefully we remember, minus the log of cos, or log of sec. Tan squared, well, tan squared is sec squared minus 1. They're both standard integrals. So sec squared goes to tan, 1 of course goes to x. Okay. Tan cubed. Okay. Again, it's playing around with that even power there. I'm going to factorise out the tan. It leaves me with sec squared minus 1. And I can rewrite that now as two integrals. The first one is tan x sec squared. But because I'll always end up with sec squared, I'm using that trig identity, and the derivative of tan is sec squared. So I can always do a substitution with the first integral. The second integral will just be tan to the power of something, which hopefully I'll have a technique for. But I will have reduced the power. See, the original one was to the power of 3, it's now to the power of 1. So every time I apply the idea, the power should go down. So u equals tan x. So I've got just u du, half u squared plus the log of cos x. And we get half tan squared plus log cos x. Tan to the 4 then, what am I going to do there? I can still do it by factorising the tan squared. Notice it's actually the second one I'm thinking of as the factorising the tan squared, because then that I change to sec squared minus 1 every time. Split it up into two integrals. The first integral, so it's the same as the other one. First integral I can do it by substitution. Second integral I've reduced the power down. And tan, the second one now, tan squared, I can do. So u equals tan x sec squared, get u squared du, but also tan squared. And so we end up with a third u cubed, and we saw before that the integral of tan squared was tan x minus x. If I had tan, did I do tan to the 5? But if I did tan to the 5, I'd still do the same thing. I'd go tan cubed times sec squared minus 1. Split it into two integrals. First integral, I can do a substitution. The second integral, I've reduced the power to something I can deal with. So with the tan ones, it doesn't matter whether the power's odd or even. I'll just do that every time. So tan, not too bad. Sec and cosec, again, I'll just look at sec. Cosec's basically the same technique. Sec to the power of 1. Now, you're going to look at this and think, I would never have thought of that. And you're right, you wouldn't have. But you will now that you see it. Because it's obvious what you're going to do. There you go. I'm going to multiply top and bottom by sec x plus tan x. Obvious. Because something clever happens when you do that. The top of the fraction becomes sec squared, which is the derivative of tan. And the second term becomes sec tan, which is the derivative of sec. So you just have derivative on function. So it's the log of sec plus tan. So the integral of sec is just the log of sec plus tan. As usually the question is, how would you think of that? And again, you wouldn't. But now you would, because you've seen it. Again, sec x, is it on the standard integrals? Integral, no. No, it's not on the standard integrals. It's another one of those ones where you might end up just remembering it. Okay, so there's sec. Sec squared, of course, is a lot easier to do. It's a standard integral. Tan x. Sec cubed. Sec cubed. Okay, I'm going to break it up into sec and sec squared. Now, why do that? I can do a u equals sec x now, because the u of sec x is sec x tan x, but the v is sec squared. Oh, he's doing it by parts. I've got two functions multiplied together, and one's not the derivative of the other. So I'm doing it by parts, essentially. So sec x becomes sec tan for the du. Dv is the sec squared. That becomes tan. So we get uv sec tan minus the integral of v du. So sec tan squared. Now how are we going to do it with sec tan squared? What we're going to do is change the tan squared to sec squared minus 1. And then the integral becomes the integral of sec cubed plus the integral of sec. Well, we know the integral of sec is the log of sec plus tan now. Sec cubed, hang on, that was my question. So now I think of it like an equation rather than when we're saying the integral of sec cubed is equal to sec tan minus the integral of sec cubed plus sec. So therefore 2 lots of sec cubed is sec tan plus the log of sec plus tan, and so sec cubed is half of all that. Basically, odd powers of sec, you'll end up using parts to do it. You'll end up using parts. Sec to the 4, I can split it up as sec squared. One of those sec squareds I change to 1 plus tan squared, and I can just do u equals tan x. U equals tan squared, the u's to sec squared. So 1 plus u squared, and there it is. So the even power is a lot easier because I can always factorise out a sec squared, leaving me with sec squared to the power of something. That sec squared I can change to 1 plus tan squared. You can do a substitution, u equals tan x. So that's why I say you really hope for an even power. Alrighty. Well,